I'll create a polished, cohesive script based on common AI research topics. Here's a professional-grade educational video script about transformer architectures. Ever wonder how AI systems understand context across thousands of words? The answer lies in a revolutionary architecture that's reshaped modern AI, the transformer. Today, we're diving deep into the mechanics of transformers, exploring how they process language, why they outperform older models, and what makes them the backbone of today's most powerful AI systems. Before transformers, recurrent neural networks, RNNs, dominated natural language processing. But RNNs had a critical flaw: they process text sequentially, creating bottlenecks for long-range dependencies. Imagine trying to understand a complex story one sentence at a time, never seeing the full picture. That's the challenge RNNs faced, leading to issues with context retention and computational efficiency. Enter the transformer, introduced in 2017 by Google researchers. This architecture abandoned recurrence entirely, replacing it with self-attention mechanisms. Let's break this down. Each word in a sentence dynamically interacts with every other word, creating a network of relationships. This allows the model to weigh the importance of different words relative to each other, capturing context in a way previous models couldn't. Here's the technical heart of the transformer, the self-attention layer. For every word, the model generates three vectors: queries, keys, and values. Think of queries as what are we looking for? Keys as where is that information stored? And values as the actual data we need. The attention score is calculated by taking the dot product of queries and keys, then applying softmax to normalize these scores. The final output is a weighted sum of values, creating a rich contextual representation. But wait, how does the model know word order? Unlike RNNs, transformers don't process text sequentially. To preserve positional information, they use positional encodings, mathematical representations that add sine and cosine functions of different frequencies to word embeddings. This allows the model to distinguish between cat sat on the mat and Matheon sat cat through these learned positional patterns. Each transformer block contains two main components: the self-attention mechanism and a feed-forward network. The feed-forward network applies a series of linear transformations to the contextualized embeddings. What's remarkable is the depth of these networks. Modern models like GPT-3 have up to 100 layers, each refining the representation through these parallel processing steps. One of the transformer's greatest strengths is its parallelizability. Unlike RNNs that process text sequentially, transformers can analyze entire sentences at once. This architectural choice enables massive scaling. Today's models process billions of parameters, achieving state-of-the-art performance on tasks from machine translation to code generation. So what does this mean for the future of AI? The transformer architecture has unlocked new possibilities in language understanding, enabling models that can write, code, and even reason. As researchers continue to refine these systems, through techniques like sparse attention and efficient transformers, we're witnessing the next frontier in artificial intelligence. The next time you interact with an AI, remember, you're engaging with the legacy of this groundbreaking architecture. If you want to explore the math behind self-attention or see how these models are implemented in code, check the links in the description. And don't forget to like, subscribe, and join me next time as we unravel the mysteries of the latest AI breakthroughs. This script maintains technical depth while ensuring smooth flow, uses conversational language for audio consumption, and provides clear explanations of complex concepts. The structure balances educational content with engaging presentation, meeting the requirements for a technical audience.